So in this video, I'm going to start talking about chapter 4, and we're going to start the chapter 4 with friction. So friction, I mean, in this section is friction between the two solid surfaces. So there's a friction force. You can have a friction force in a fluid, such as you can have an air resistance, air drag force that's in a fluid, or in an oil, you have a viscosity. Those are friction forces, but that's not something that we're going to discuss in here right now. What I'm discussing about friction force is between two solid surface when they're in contact. So let's get into the note here. All right, friction force. Friction. And what I mean friction in this section is between two solid surfaces. So it's not so straight. When you look at two solid surface that's in contact, and then when we look at in close-up view, they always have on the surface, you always have some kind of irregularities. You're never going to have a perfectly flat surface. Even the graphene we think that is very, very flat too, they're still going to have some kind of bumpiness because they're made of molecules. So let's see, this is an exaggerated view of irregularities, physical irregularities, or it could be chemical too, right? Chemical bonding, it may have a chemical bonding too. So when you have these two irregular surface meet, they're not made perfectly, they're not flat for it. They're not perfectly flat. So there's this zigzagginess that's they have, and then when they're in contact, right? When they push against each other, so so it could be like this. You push, you push, something like that. So you could have two surfaces that's in contact, and then you push together, then it kind of locks, or it makes it really hard to move smoothly. And that's what the friction force is. And remember how the friction force is applied? Friction force is applied. How does the friction force apply? So let's say this is an object, right? And then it's on the surface here. So this is a close-up view. What's happening here? The close-up view. Close-up view. And when you have a object that's, let's say it's, there's a push force. So the force is, there's a force to push this object to the right. Then there's gonna be friction force applied in this direction, right? This is gonna be the friction force. Friction force is so friction force here is to either to oppose the motion. So you have a friction force. There might be a friction force when the object is in motion, when they're in contact with the solid surface, and then or to oppose. You could have a friction force even though when you're not moving, oppose the exerting force. And then the friction force is contact force, and then it's parallel to the surface. So I like the support force that's always applied perpendicular to the surface because the support force or normal force is that wants to push back upward. But friction force is to oppose the motion, oppose the exerted force along the surface. So it always applied parallel to the surface. So this is the review for the friction force that we learned about which direction it applies. Let's study more about the friction force. Let's see. So from this close-up view, you can see that irregularities between the two contacts, the two surfaces that's in contact, it arise the friction force. So depends on the type of a surface you have. Sometimes you have two contacts have a slippery condition. Sometimes it's a lot harder, like it's a lot more bonded together, harder irregularities. So you can, I hope you can see that friction force depends on friction force depends. So friction force depends on the two factors. One is depends on material property. Properties of two surfaces in contact. So the material properties of two surfaces in contact. So depends on the type of material, the friction forces change, which makes sense, right? And then friction force also depends on another factor, which is depends on support force, normal force. These are the thing that friction force depends on. You can see that, so two materials make sense. And the support force, although friction force applies parallel to the surface, but the more you push against each other, you're going to have a bigger friction force. If you don't push as much, you're not going to have as much friction force in this motion, parallel to the surface motion. So how much you're pushing down, how much is surface is pushing you up, um, depends on, that changes the magnitude of friction force. So these are the only two things that friction force depends on. Again, depends on, and, okay, materials properties of two surfaces in contact, and support force. Okay, so that's very important. Let's see. How about How about this right now? The pen is at rest on my hand. Is there any friction force applied? Is it at rest is because there's a friction force? There's no friction force because you don't push it or anything. But how about this? When the object is at rest, another question is this. So, right, we don't know. Let me see. You can see that, so when the object is at rest first, I have an object here, right? And then it's on the surface. It's connected to the measure to measure the force. So, and then I apply a push force. Push force to the right. Okay. When you apply a force and force, sometimes it doesn't, you gotta apply big enough force and then it starts sliding. It won't, so initially it may not move. That's because even though you're applying a force to trying to pull and pull and pull, and it doesn't move, that's because of friction force. There is a friction force applied. That's why, because of friction force. Even though you have a push force applied. And then you push it, push it, push it, push it. You push it harder and harder and harder. You increase the push force. Then at certain moment, it may start sliding. When it just starts sliding, is there any friction force? Right, even though it starts sliding, you still have a friction force. So even after start sliding, friction force doesn't disappear after you start sliding. You still have a friction force. So how is it? How are they applied, right? Let's see, I'm going to try and draw graph here. And then, so this is the x-axis represents the push force. And the y-axis represents the friction force. All right. Let's say, for example, in example up here, right? I'm pushing, 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 and it doesn't move. So when I push, let's say 2 Newton to the right, and then if the object doesn't move, how much is the friction force and in what direction? So if I say I'm pushing the object to the right, and then, so question here. Object is still at rest. And then at that time, there is a push force is applied, let's say 2 Newton to the right. How much is the friction force? And then in which direction? Yeah, it should be, if it's not moving, you should have a push force 2 Newton, then you're gonna have a 2 Newton friction force. I should change the color. You should have a 2 Newton friction force. And then the direction should be to the left, opposite direction to oppose the exerted force. So as you can see that you increase push force. As you increase the push force, friction forces also increase linearly, and then it's going to be equals to each other. But at one point, if you exert enough push force, you're going to break those bonding, the bonding in between the two surfaces, then object starts sliding. So when it starts sliding, do you think the friction force should change when it starts sliding? Do you have an increase in friction force? Depends on the speed. Faster you go, do you think the friction force decreases, increases? Does it change after it starts moving? No, because the friction force only depends on material properties of the two surfaces, right? And the support force. So when it starts moving, you exert bigger and bigger push force. It doesn't mean material properties between the two surfaces change. They just got unlocked. And then the support force doesn't change. And then even though it starts unlocking, you still have those bumpiness with each other. So you're going to have the friction force still applied. It's not going to suddenly disappear just because you unbounded the two surfaces that stuck together. You're still going to have the bumpiness. So you're going to still have a friction force. And the amount of friction force doesn't depend on, it only depends on the two material property of the two and the support force. So even though you increase the push force, now the friction force after it starts moving, it's going to stay rather constant. So in this graph, from here to here, object is at rest. So you increase the push force harder and harder and harder. Friction force is there to resist it, and then object doesn't move. But after you exert enough push force, then it starts sliding. So from here, after that, object is in motion. But just because object is in motion, now the friction force doesn't change. Because it only depends on the material property of the two. So we say, let me see. Here, when the object is at rest and the friction force that's applied on the object that's at rest, we call this as a static friction. And when the object is in motion, the friction force that's applied in the object that's in motion is called kinetic friction. And I hope you see that's not what I meant. I hope you see that this kinetic motion is constant. It's rather constant. It doesn't change the value as you increase in push force, right? But then a static friction increases as you increase in push force. And what's interesting, another thing that I drew here that I haven't mentioned still is this drop. So when the object starts, immediately after it starts sliding, immediately before it starts sliding, so you push harder and harder and harder, and then the friction force drops just a little bit. And then you have a kinetic friction, typically. That's because that this friction force is like bounded. And when this, it becomes just like force enough, you push enough that it becomes unbounded, it becomes a little bit easier to start sliding. And then after that, the irregularity of the surfaces, two surfaces applies the kinetic friction. So you have a static friction increases, and then you have a maximum. This is going to be the maximum static friction. And usually the maximum static friction is higher than this kinetic friction. So the value that when it just starts to, start sliding is called the maximum static friction. So the static friction is not constant. So it changes as you, depends on how much you push. But this maximum static friction is unique to those two materials. It only depends on those two materials at that normal force, with those normal force that's applied. Then after that, passing that maximum static friction, it starts sliding and it drops, the friction force drops a little bit and becomes constant. So let's just write it here. So there is two kinds of friction. There's two kinds of friction. One is called static friction. For the static friction, object is at rest. Is at rest. So, and then, for example, if push force is at 5 Newton and then apply to the right, then static friction force. Static friction force is 5 Newton applied to the left. If F push force is applied 8 Newton to the right, then static friction force is 8 Newton to the left. So that's the static friction force. Then you have, and then if it exceeds, if the push force, when the push force exceeds the maximum static friction, then friction force changes into kinetic friction. So in the case of kinetic friction, object is in motion and the value, it's rather mostly constant. Kinetic friction, the value of a kinetic friction is mostly constant. It's not perfectly constant. It may vary a little bit, but it's mostly constant and is less than maximum static friction. So these are the characteristics of two types of friction force, static friction force and a kinetic friction force, as we have just seen it in here, right? All right, sorry, like that. Okay. My question. Question is, does friction force, especially kinetic friction force, does it depend on the speed of the moving object? No. Does it depend? No. Does not depend. Does not depend on the speed of the moving object. How about what if you change the contact area? So let's say rather than putting the object like this on the surface, just put it like this. So if we decrease the contact area of the two surfaces, do you think does it change the friction force? Does it depend on the contact area? No, it does not depend on the contact area of the two surfaces. My kids are going crazy. Let me show you the demonstration here. Static. So here, I have here. I have this stuffy cat. It's not a real cat. And here you see is the scale to measure the force. What's the unit of the force? Unit of the force is Newton, right? So you're going to look at the scale that says Newton. That reads the magnitude of a force applied. So when this person pulls the stuffy, you can see that more and more he pulls, there's an increase in the push force, the pull force. And you can apply harder and harder and harder. The stuffy will move, but at one point it starts moving. You apply enough force, then it starts moving. So it's like that. Sorry, right? Let's see again. So it starts pulling, 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 and then it starts moving. Another one. So this is the close-up view. Again, take a look at pay attention to the Newton. It says Newton, and that's the one that measures the force. All right. So pull it about, what's the magnitude? Start sliding. One more time. See, 5 Newton, around 5 Newton, this stuffy starts moving. And then this is probably still hard to see. I did my best in, oops, okay. I did my best to share, to take the video, but here is another close-up, and you can see how much force is being exerted after it starts sliding. Okay, so pull. All right, please pull. Right, so about, I hope you, so again, no. So about 5 Newton, it starts sliding. And then after that, he was pulling the stuffy with about the constant motion. For the object to be in a constant motion, what if he's pulling 2.5 Newton, how much is the friction force? And what kind of a friction force is it? When the object is in constant motion, that means that it's in dynamic equilibrium. So the push force has to be equals to the friction force in magnitude. And they have to be opposite to each other so that they don't have no change in velocity, right? That means that if he pulling with the 2.5 Newton, that means that kinetic friction is in 2.5 Newton in an opposite direction. So you can see that as he pulled harder and harder and harder, the friction force, static friction force increased from 0 to 5 Newton. Then after push force has reached the 5 Newton, the friction force dropped, and then the object starts sliding. Then the kinetic friction was about 2.5 Newton. Let's see again. All right, please pull. I guess it's not 2.5 Newton. It's more like 3.5, 3 something, 3.5 or something. Yeah, it's not 2.5. It's bigger than 2.5. Makes sense. It should be just slightly less than maximum static friction. The kinetic friction force should be slightly slower. All right, so this is going to be the end of this video, and I'm going to see you guys in the discussion.